All right, section 412, tension force, and worksheet, do number 1, number 2, and number 1, number 2A, only do 2A, and number 3. I want you to ignore friction on this worksheet. And let me see, I'm getting my notes out here. I just printed them. I like this. This is an interesting thing I wanted to show in. Usually, this is where I normally begin the second semester every year. So we're a little bit late getting this because of being Zoom all year. I usually start it. We don't normally do it in the first semester, but I wanted to go over this, and I'm skipping a little bit of material we might go over some details that we would have gotten, but you don't need it for this. But tension involves the force transmitted through a string or a rope. And there's some interesting things about this I'll go over. But one thing I'll just tell you, like imagine that you had, this is 412, and I had to put a new little note section for you. But let's just say here you have like a concrete block. And let's just say that you tie a string onto that. And here I'll put like a feather. All right, a feather there in a concrete block. Now, let's think about this for a minute. You know, if I were, this could be like a little string there. If I pulled with a rope in this direction with a certain force, like, I could put whatever, 200 newtons, I pulled this direction, it would drag that behind it, right? There'll be a certain tension in that rope. It will be the force transmitted through the rope. Oh, and it came apart, but oh well. It'll be the force transmitted through that rope. That's called the tension. And you can measure that, by how much pull, and it will have a force. It'll have a certain number of Newton force. Every point in the rope, in the string, will have the same force on it. Be pulling both directions. That way, it'll be pulling this feather will be pulling it that way, and it'll be slowing down the concrete block that way. And that tension is going to be based on these two objects. Well, here's the point I was trying to tell you about, or trying to kind of show you here. If I pull with 200 newtons from this side, I might pull it, drag it along. You're going to have a certain tension in the rope here, and the tension here that you just pulled on. This rope will be a 200 newton tension. Well, most likely 200, a tension 200. Now, we'll call that the force, 200 you're pulling on that one. But if I were to pull on a rope on this side, what could happen? It could break, couldn't it? Easily. Like I put 200 on this side, it could break. So you see that there will still be tension there, and I won't be able to move them if I pull them that way. But if I pull the other way, I would be able to. Well, that's just kind of a little interesting thing here. But it tells you a little bit about tension to be thinking about. Let me do the first problem. Tension is transmitted equally throughout a rope. And we're going to calculate some little examples here. And these are little puzzle things that you'll see. We can do an experiment with them if we were in person. Or you might see these again in the future in physics in college. And that's why I wanted to do it. So we have a bucket. And it says that Spot is pulling the bucket west. So we'll let that be west. So I'll draw a little, how I'm going to draw a little dog. Spot. Okay, we'll just let him be Spot. And here he is, and we'll just put his, his feet would be that way, wouldn't it? Okay, his feet, he's trying to pull. Yeah, he's pulling that way. So Spot, we'll put a rope. Oh, we got to put his tail up here. So we got a rope tied to the bucket and tied to Spot's tail. And then on the other side, you have Lily pulling it. And we'll draw her. We'll put her hands there, and we'll show her with her legs leaning back this way. Okay, so and my bucket's too small. Let's put another level there. So there they are pulling the bucket across the ground. It says Spot is pulling a 2-kilogram bucket west. Lily is pulling it east. Okay? The system is accelerating east at 5 meters per second squared. So we know the acceleration is going to be 5 meters per second squared. Now, because we have east and west and all that, I'll just let that be positive. So we'll say this is the positive direction, and that's the negative direction. And it's going positive or east. I'll put east next to it. 5. The tension in Lily's rope is 75 newtons. So inside this rope, there's a 75 Newton tension. So that's what she's pulling. So the question is going to be, what is the tension in Spot's rope? And we're going to call that tension, maybe I'll call it TS for Spot. So tension in Lily's rope, TL, is 75 newtons, and the tension in Spot's rope is TS. So we want to figure out what is the tension in that rope going to be. All right. So let me get, the way we do this is we're going to make a little equation, and we're going to make a net force equation. The object we're going to be thinking about is the bucket. The net force on the bucket, the net force is equal to all the forces acting on it. The forces acting on it, you have Lily's tension and you have Spot's tension. I could call that her pulling force, but let's call that TL, just to make it easier here. We have TL and we have the tension Spot. Now, if we were looking at friction, we would also talk about the friction force. And we know it's going this way, so friction would be going that way. But we're not going to do friction. We might go back and I might talk about it, but I don't, for now this is all I want to do. All right, so the net force will equal the tension of Lily's rope plus the tension of the Spot's, the vector value. So we'll put that over here. We'll keep that as I could put MA there if I want to. Remember, F net is MA. Lily's tension is 75.0 newtons. Now, is it positive or negative? Since it's going this way, she's pulling in that direction, the same direction as the acceleration, so it's positive. So we don't really have to put a positive, okay? We can just leave it off. Spot's tension, though, is going to have to be negative because he's pulling that way. So there it is. It will be negative TS. So M to A equals 75 or minus TS, plus and negative. A is 5 meters per second squared, so I'll put in 5 meters per second squared times M is equal to 75 minus tension in Spot's rope. So now, oh, I'm sorry. I forgot to put in 2 kilograms. Okay. All right. 2 times 5 is 10. Equals 75 minus tension of the Spot's rope. So 10, now if I take away the minus 75 from both sides, I'll get 10 minus 75 is negative. 65 is the tension in Spot's rope. That would make sense because what's going on is negative means it's in the other direction. Tension is a force. You can call it tension force if you want to. Some call it FT, F tension, but I won't do that. I'm going to use it the way I did here. So negative 65 and going in that direction would be the way he's pulling it. So that is all for that first problem you need to know if you just had 2 ropes involved. But what if there were more objects involved being dragged along, like a train car? So I'm going to do one more little sample for you here. Now it says, for letter B, we have block A and block B connected. And the way they like to do these in a lot of standardized tests, end of the year state tests, they like to do this with train cars hooked together. But it'll work the same concept with this one. And you'll see one like that at some point. Block A has a mass of 50 kilograms. Uh-oh, not 5. Block B has a mass of 75 kilograms. Okay, block B is being pulled east with a force of 200 newtons. And so we're going to let that again be east, be positive. And it says block A is being pulled west 400 newtons. All right. And we'll put a little dot after the numbers, meaning they'll have 3 sig figs. Okay. Now, the question is, what is the acceleration this time of this system? And also, what is the tension in this rope that's connecting them? We'll just call it tension. It's only one tension, so we'll just call it T. Now, if you had A, B, C, 3 cars, you could have 2 tensions. And this worked for that as well. And you're going to probably see one like that. It might be fun to do one like that later. So there really are 3 things that you normally need to answer in a question like this. One is, what is the acceleration of the system? One is, what is the tension in the ropes connecting them? And the other one is, what direction will it move in or accelerate in? And that ought to be kind of obvious in this problem, but sometimes it is not known which way it's going to move. Now, if we're pulling 400 this way and 200 this way, obviously it's going to go this way. Pull 400 tug of war, it wins. But you'll see what I mean, that sometimes we're not given all the information to know. So, since we know it's going to go that way, and we'll say in the negative direction, all right? And positive will be the east. So, when I calculate my answer, my acceleration, it should be negative, meaning it's going to go in the negative direction. I'm going to let that direction be negative, it's going to go that way. If you ever did a problem, and say you set everything up, like I did, positive that way, negative that way, and you say, okay, it's going to go that way, my acceleration will be negative. But if for some reason your answer came out to be positive, and you know you did it right, then what it means is your math is right, but it went in the other direction, okay? So that's a weird thing. It won't happen on this one, but it will probably at some point, or I'll do one in the class or online. Okay, so here we go. Now, how will we do this problem? We're going to make 2 net force equations, one for A and one for B. So for A, for box A, the net force on A is equal to what? What things can determine A? Only look at the ones that are directly on it. It'll be the 400 Newton force. Maybe I'll call it force 400. I don't know. We'll give it some name. I like to sometimes give it a formula before I put the numbers in. And then it will also be tension. Now, the force 400 is going to be negative because you know it's going that way. And the tension is actually going to be positive. See, tension is actually slowing this thing down because it's dragging this behind it. If I were to cut that, obviously it would accelerate even more. So this tension is going to be acting the opposite direction of of 400. Okay, so negative T, negative F and T. So the net force on A, MA, equals negative 400 newtons plus, and just T. So there's nothing to put. T is positive. Or we can say T minus 400. Oh, and I need to put in one more bit. I know it's 500 kilograms. 50 kilograms, MA, 50 times A, I'll just make it 50A, equals negative 400 plus T. I like to write it as T minus 400. That might be a better way to write it. Okay, so you might be thinking, wait a minute, what have we done? Well, we have an equation with 2 unknowns in it, an A and a T. But guess what? We can make another one with box B. Can you see where we're heading? In a minute you'll see, and you'll be very happy. And think, oh, you might think, oh no, but if I had told you in the beginning, you'd be scared. But after this, you'll see it's not too bad. Okay, the net force on box B is going to equal, now we have the tension force, and we also have the 200, so we'll call that force 200. Now, which one is positive and negative? The tension this time will be negative. Now for B, it's going to be pulling it along. So tension is going in the negative direction, but the 200 will be going in the positive direction. So that'll be positive. So that on B, MA is equal to negative T plus 200 Newton. And so I'll put in my numbers as well. 75A, 75 for the M, is equal to, and I can make it to, I just like to write it that way, 200 minus T. I like to have it, T minus 400 and 200 minus T. I think it's easier to look at it to understand that way. All right. So now can you see what we have put ourselves into? We have a system of equations, and we can now combine them. There's a couple of ways to do it. You can add one to the other, multiply by a common multiple and get rid of one of them and solve for the other one. Or you can use substitution. So we can use cancellation or substitution. I'll do the substitution, is probably easier. But what was I going to tell you? Oh, it is really important in the very beginning that you say negative, positive. Or if you want to do it the other way around, if you let that be positive and that be negative, then you got to be consistent when you make all of your equations. If you don't stay consistent, you'll get some kind of weird looking answer. All right, so here we go. Let's just see. It's going to be easier to solve for t, I think, on this side. I'm going to say t would equal 50a plus 400 newtons equals t. Doesn't that make sense? If 50a equals t minus 400, then 50a plus 400, if I put plus 400 on both sides, you'll cancel that out. 50a plus 400 equals t. Now I can take that and substitute it in for t right there. See, even though you have two equations, a and a have to be equal, and t have to be equal. So I'll substitute it in here. Maybe I'll do it down here just to get out of the, if it don't fit. 75 times a is equal to 200 newtons minus, I'm going to use brackets here, t. Instead of t, I'm going to put in 50a plus 400 newtons. Now be careful. Notice I put brackets around it because that negative applies to both. Next step, I will take a little bit more algebra here. Just 200. I'll leave off the n. Minus 50a and minus 400 newtons. Now, okay, let's collect all the terms. So to get rid of the 50, I got to add 50 to both sides. 50a plus 50a. So that means 125, right? Yeah. 125